Okay, so our discussion will focus on the relationship of mass and energy in a nuclear reaction and their nuclear or the nuclear binding energy. So the energy change accompanying a nuclear reaction can be calculated from the relation delta E is equal to C squared multiplied by delta M, where delta M is the change in mass and it is actually the mass of products minus the mass of reactants. And delta E is actually the energy of products minus the energy of reactants. And C is actually the speed of light. In a spontaneous nuclear reaction, the products weigh less than the reactants. And in this case, the energy of the products is less than that of the reactants, and energy is evolved to the surroundings. So to obtain a more useful form of the equation delta E is equal to delta mc squared, we substitute for C its value in meter per second. So we have here the value of C, which is the speed of light, and it is 3.00 times 10 raised to 8 meter per second. Okay, we just multiplied it by itself. So we have 9.00 times 10 raised to 16 meters squared per second squared. And we retained the delta M. But we have here 1 joule is equal to 1 kilogram meter squared per second squared, as well as 1 meter squared is equal to 1 joule per kilogram. So we have delta E is equal to 9.00 times 10 raised to 16 joule per kilogram multiplied by delta M. So this equation can be used to calculate the energy change in joules if you know delta M in kilograms. Ordinarily, delta M is expressed in grams, and then delta E is calculated in kilojoules. So the relationship between delta E and delta M in these units can be found in using conversion factors. Delta E is equal to 9.00 times 10 raised to 10 kilojoule per gram multiplied by delta M. So we should take note on this. Uh, okay, so we have here an example from the radioactive decay of radium or radium-226 with alpha emission. It produces uh, radon-222. Calculate the delta E in kilojoules when 10.2 grams of radium decays. So we have here the given. So yeah, basically we have the nuclear reaction and the mass of radium-226, which is 10.2 grams. So and we have the nuclear masses. Yung table 18.3 will be posted on Schoology. And we are asked for delta E. So, na-extract na yung table 18.3. So, we have here helium. So, ang gagamitin lang natin is yung with atomic number 2 and with a mass number of 4. So, we have 4.00150 atomic mass unit for helium. And we have radon with 221.9703 atomic mass unit. And we have also the radium 226, which is 225.9771 atomic mass unit. So we can also observe that one atomic mass unit is also equivalent to its gram per mole. So for example, this helium 4, this atomic mass has 4.00150 grams per mole. All right. So we have here, so the strategy. So again, yung delta M is equivalent to or is equal to the nuclear masses of the products minus the nuclear masses of the reactant. So, and then after we will find delta M for the decay of 10.2 grams of radium 226. And then we will be able to determine the delta E by substituting it into the equation shown before. So we have here. So again, products minus reactants. So we have on the reaction we have helium and or in the reaction on the product side we have helium and radon. So helium we have again we have 4.00150 plus the mass atomic mass of radon which is 221.9 uh 703 grams minus the mass of the reactant. So we have here uh delta M is equal to 0.0053 grams per mole of radium 226. So we also have a given mass of radium, no? So we need to convert this one. So we have 10.2 grams of radium multiplied by in 1 mole of radium we have 226 grams radium multiplied by the delta M from the delta M for 1 mole from the nuclear reaction. So in 1 mole, we have negative 0.0053 grams. So our delta M for 10.2 grams will be negative 2.4 times 10 raised to negative 4 grams. So again, yung una, delta M for 1 mole. So yung pangalawa is delta M for 10.2 grams of radium. So we can now be able to calculate the delta E. So given ito kanina, okay, 9.00 times 10 raised to 10. Again, it is the C squared. Now, if you can recall, this is the C squared, the speed of light squared. Okay, times 10 kasi naging kilojoule per gram na siya. So, and it will be multiplied by delta M, which is the negative 2.4 times 10 raised to negative 4. So we have here delta E is equal to negative 2.2 times 10 raised to 7 kilojoules. It should be kilojoules. So we have here the nuclear binding energy. So it says here that it is always true that a nucleus weighs less than the individual protons and neutrons of which it is composed. Consider, for example, the lithium-6 nucleus, which contains 3 protons and 3 neutrons. So according to table 18.3, 1 mole of lithium-6 weighs 6.01348. And in contrast, the total mass of 3 moles of neutrons and 3 moles of protons is 6.04785. So again, itong 6.04785 is the predicted one. So it is predicted based on the calculation from this. So 3 times the mass of neutron. So again, kasi nga sa lithium-6 we have 3 neutrons and 3 protons. Okay, so 3 times the mass of neutrons, which is the 1.00867, plus the number of protons multiplied by its mass, which is 1.00728. So we have here 6.04785. So it's the predicted one. But we have, based on the table, we have 6.01348 as the mass of the lithium-6. It's actually weighed experimentally. Okay? So, again, ito yung actual mass. So clearly, 1 mole of lithium 6 weighs less than the corresponding protons and neutrons for the process. So we have uh, delta M, no? So yung predicted minus the actual mass is actually uh 0.03437 grams per mole lithium, or atomic mass unit. So it is actually called, or yeah, it's actually referred to as the mass defect. So bakit nga ba may mass defect? Okay? So the corresponding energy difference is, so for example, we have the the delta M, which is 0.03437. Okay? Ito kasi yung uh, amount which is converted to energy when the nucleus was formed. Okay? Again, the mass defect, bakit may mass defect? Kasi, or bakit mas malaki yung predicted natin over the actual? Kasi, kasi yung mass defect is actually converted to energy when the nucleus was formed. So we can be able to, from that, we can be able to calculate the amount of energy needed, no, to form that particular nucleus. So from this equation, we have delta E, okay, equals 9.00 times 10 raised to 10 kilogram per, or kilojoule per gram, multiplied by the mass defect, or delta M. We have 3.09 times 10 raised to 9 kilojoule per mole lithium. And this is actually, or this energy is actually referred to as the binding energy. So it says here that it follows that 3.09 times 10 raised to 9 kilojoules of energy would have to be absorbed to decompose 1 mole of lithium 6 nuclei into protons and neutrons. So ganun din siya. This is the amount of energy needed to form or to decompose that particular nuclei. So we should take note that it really takes a lot of energy to blow a nucleus apart. Okay, so we have here an example. So calculate the binding energy of carbon 14 in kilojoules per mole. Okay, so we have, uh, let us recall, in carbon 14, it is actually made up of 6 protons and 8 neutrons based on the nuclear reaction. Okay, so using the table 18.3 again, we will be able to calculate for the delta M. And then after that, we will now substitute it into the equation to find delta E in kilojoule per mole. So again, so we have here neutrons, H and C. So on this part, for H, we will use this one, 1.00728, because atomic number 1 and mass number 1, based on the reaction. And for carbon 14, we will use 13.99995. Okay, so we have here the solution, delta M. So kanina we have 6 hydrogen, no, multiplied by its mass, with 1.00728, plus 8 neutrons, 8 multiplied by the mass. So again, remember, this one is actually the uh, mass of the products, and we will deduct it to 13.99995, which is the mass of carbon 14. So from that, we can now be able to substitute it into the equation. Uh, we will have delta E is equal to 9.00 times 10 raised to 10 kilojoule per gram times the delta M, So we will have 1.02 times 10 raised to 10 kilojoule per mole. So just a reminder, wag na wag nyong i-round off yung atomic mass. So you should write the complete atomic mass. Again, do not round off the atomic masses of the atoms. The binding energy of a nucleus is, in a sense, is a measure of stability. The greater the binding energy, the more difficult it would be to decompose the nucleus into protons and neutrons. Again, malaki kasi yung binding energy, so mahirap siyang i-decompose, mahirap siyang i-break into protons and neutrons. So, as you might expect, the binding energy as calculated above increases steadily as the nucleus gets heavier, containing more protons and neutrons. So, a better measure of relative stabilities of different nuclei is the binding energy per mole of nuclear particles or nucleons. This quantity is calculated by dividing the energy per mole of nuclei by the number of particles per nucleus. So this one is for example. So kanina meron tayong uh, 3.09 times 10 raised to 9 kilojoule per mole lithium 6. So we have 6 nucleons, no? Kasi we have 6 protons and 6 neutrons. Okay, so in 1 mole of lithium 6. So we have 5.15 times 10 raised to 8. Same as through with carbon 14. So since we have 1.02 times 10 raised to 10 kilojoule per mole. So in 1 mole of carbon 14, we have 14 mole nucleons. So finally we have 7.29 times 10 raised to 8 kilojoule per mole. So we can actually uh, express this one into mega electron volt or the MeV. So in 1 mega electron volt or MeV, we have 1.6 times 10 raised to negative 13. So this one. For example, the lithium 6. Oh, so we have here 5.18 or 5.15 times 10 raised to 8 kilojoule per mole. So in 1 kilojoule, we have 1,000 joules. So the conversion factor of 1 mega electron volt has 1.6 times 10 raised to negative 13. And in 1 mole of lithium 6, we have 6.022 times 10 raised to 23 or 23rd of lithium 6 atoms. So in 1 lithium 6 atom, we have 6 nucleons. So therefore, we have a binding energy of 5.345 mega electron volt per nucleon. So usually, ganito siya i-expressed in mega electron volt per nucleon.